Hi, I'm Daniel.
I'm Jake.
And I'm Micah, and today we're going to be talking about the physics of a curveball. There are two principles that we must explore before analyzing a curveball. These two principles are the Bernoulli principle and the Magnus effect. Bernoulli's principle relates the pressure of a fluid to its elevation and its speed. Bernoulli's equation can be used to approximate these parameters in water, air, or any fluid that has very low viscosity, or a fluid that is not thick. The Bernoulli equation states that for an ideal fluid, a fluid with zero viscosity, constant density, and steady flow, the sum of its kinetic, potential, and thermal energy must not change. These constants allow for a predictable relationship between the velocity of the fluid, its pressure, and its elevation. When the speed of a fluid is high, its pressure is low. Conversely, when the speed of a fluid is low, the pressure is high. They're inversely proportional. This picture shows the correlation between the open area, or low pressure, to a high velocity, and the correlation between a tight area, or high pressure, and a low velocity. Specifically, this principle relates to the air surrounding the baseball during its flight. The pitcher puts topspin on the ball, causing the air around it to become disturbed. The friction provided by the stitches of the baseball causes a thin layer of air to move around the spinning ball, causing the air pressure on top of the ball to be greater than the air pressure on the bottom. This pressure forces the ball downward. The Bernoulli principle is a major component in the Magnus effect, with the addition of Newton's third law. The Magnus effect is what causes a 12-6 curveball to dive toward the ground. A 12-6 curveball, also known as perfect topspin, can be seen in these videos of pitcher Clayton Kershaw. The Magnus force is what pushes the ball downward, as the ball spins against the airflow on the top and with the airflow on the bottom. The disturbed airflow on the top causes more pressure on the top of the ball. Newton's third law explains that when the ball first pushes on the air will push back on the ball with the same force. Accompanied with the Bernoulli principle, the increase in downward velocity will cause an effective curve. Here's a picture of the Magnus force of a fastball, as the disturbance on the underside of the ball pushes it upward.
Now we're going to look at the curveball in action, and we're going to start with the pitcher's perspective. In baseball, a pitcher is able to control the curve of a pitch by putting spin on the ball as the ball leaves his hand. As the pitcher spins the ball, the spin itself disturbs the air around the ball, essentially making the air uneven at all points around the ball. The spin causes the air on one side of the ball to move much faster than the air on the opposite side. Using this, the pitcher can dictate which way the ball turns based on the spin that he puts on the ball. For example, if the pitcher spins the ball to the left, it will turn that way as well because there is far less pressure on the left side of the ball. This is where the Magnus force comes back into play. With the Magnus force, which the equation is 1/2 times Cl times P times A times V squared times omega cross V, we know that Cl, P, and A are always going to be constant with a standard Major League Baseball. So, the Magnus force for a curveball depends on how fast the pitcher throws the ball, which is V, and the angular velocity, or how fast and in what direction the ball is spinning of the ball. The ball will curve whichever way it is spinning because the airflow on that side of the ball is less distorted than anywhere else, causing the ball to travel that way. The pressure on the opposite side of the ball, as we mentioned earlier, is much higher, forcing the ball in the direction that it's spinning. The pitcher is able to control and predict where the ball will end up based on how much spin he puts on the ball, as more spin will curve and push the ball further in the direction which the spinning is intended to go. In terms more germane to the sport, a pitcher's curveball is only as good as his ability to put loads of spin on one side of the ball as he releases it, while simultaneously being able to control and predict where the ball will end up. That being said, the curveball can be very useful for a pitcher who can consistently deliver the ball into the strike zone, because a curveball appears to warp in the eyes of the batter, making it far harder to hit than a fastball when thrown correctly, and we'll talk about that in the next slide. Now we're looking at the curveball in action from the batter's perspective. So, from the perspective of the batter, curveballs are often reported to look as though they are not curving at all. In fact, batters commonly perceive that a curveball begins on a straight path, and that at some point between leaving the pitcher's hand and leaving the plate, the ball breaks at a specific point, and the curving takes place. However, as we explained in the last slide, the curve truly does begin as soon as the ball leaves the pitcher's hand. Throughout the course of a single baseball pitch, batters switch from foveal or central vision to peripheral vision, and then back to foveal just before they hit the ball. The issue for batters lies in the peripheral stage, which usually begins about 20 feet into the pitch. Foveal vision allows humans to recognize the curve of the ball, but the initial foveal stage is very brief. In the peripheral, however, the batter is unable to recognize the curve anymore, and the ball looks as though it is moving straight forward until just before the batter must swing, and only then can the batter's eyes switch back to foveal. This is why batters in baseball commonly describe a curveball as one breaking moment, despite the fact that the ball curves from the moment that the pitcher actually lets go of it. Now we're going to look at 3 diagrams which show this. So, the top left image shows the initial stage of the pitch. The ball has the most straightforward velocity here out of any point in the pitch. Although the ball looks as though it will continue going straight, the ball does in fact curve, which can be seen in the middle picture. This image shows the peripheral stage for the batters. Their eyes are unable to recognize the curve at this juncture, which explains why this diagram shows such an abrupt curve as opposed to a continuous, smoother curve. Because as we see in the top left image again, the batters perceive it as straight until they have this very brief breaking moment. In the third and bottom picture, we see that breaking point. The ball appears much more forward moving than in stage 2, but less so in stage 1. The batters now return to foveal vision, leaving them with a very brief window of time to adjust from the massive curve that they see between stages 1 and 3, and to recognize how significant the ball's total curve was and to try and hit it.
There are 3 main forces aside from kinematic factors that impact the trajectory of a pitch. The first one is drag force. The drag force refers to the resistance caused by the motion of an object through a fluid, including air. This force acts opposite to the direction of the oncoming flow velocity. The drag force thus measures the relative velocity between the body and the fluid. The equation for the drag force is the force of drag equals 1/2 times the drag force coefficient, which varies along with the speed of the object and is typically between 0.4 and 1. The density of the air, which is about 1.225 kilograms per meters cubed, times v, which is the velocity of the ball, times a, which is the projected cross-sectional area of the object, perpendicular to v. Another force that impacts the pitch is the Magnus force, which was explained earlier. The equation for the Magnus force is 1/2 times the coefficient of lift times the air density times the cross-sectional area of the ball times the velocity of the pitch. The final non-kinematic force that impacts the flight of a baseball is gravity. Gravity is the force that attracts 2 bodies towards one another. The more massive the object, the stronger the gravitational pull that object possesses. Also, it causes objects to have weight by multiplying the mass of an object by the gravity. On Earth, gravity is about 9.81 meters a second squared, at least in the Midwest where we live. Gravity is what causes the baseball to fall down after the pitch has been thrown. Baseballs, like many other things that fly, rely on aerodynamics. For a slider, which is a variation of a curveball, the force of aerodynamics is equal to the coefficient of lift times 4/3 times the quantity 4 times pi squared times the density of air, which is, again, 1.225 kilograms per meters cubed, times the spin of the pitch, which is measured in revolutions per second, times the velocity of the pitch, times the radius of the baseball, for which a standard MLB ball is about 3.65 centimeters, cubed. Using Newton's second law, we can calculate the acceleration of the baseball with mass m. With the slider, the baseball moves horizontally, roughly following a curved path, as seen in the image in this slide. This curve has a certain radius r, which we can calculate using the formula r equals v squared divided by a. Using trigonometry and the Pythagorean theorem, we can solve for yd, which is the horizontal displacement from the center of the plate. We can set up the equation r squared equals d squared minus the quantity r minus yd squared, with d being the distance from the pitcher's mound to home plate to solve for the horizontal displacement. When we isolate horizontal displacement, we get yd equals r minus the quantity r squared minus d squared, all to the power of 1/2. This set of formulas and the equation will help us calculate the final horizontal displacement of the ball based on the pitch velocity as well as the baseball's rotational velocity. Here are a couple clips of MLB pitchers throwing curveballs in action. Though some pitchers have slightly different styles, mastering a curveball can make a pitcher always keep the opposing hitters on their feet.